Problem number 12 asks us to use the chain rule for partial derivatives to find the partial derivative of r with respect to x and the partial derivative of r with respect to y. I'm going to do partial derivative of r with respect to x, and I'm going to let you then follow that model to do the partial derivative of r with respect to y. So first we take the partial of r with respect to each intermediate variable and multiply that by the partial of the intermediate variable with respect to x. So we're doing the partial of r with respect to u times partial of u with respect to x plus partial of r with respect to v times the partial of v with respect to x plus the partial of r with respect to w times the partial of w with respect to x. Okay. Now we need to calculate some values to plug into this. We know that x equals y equals 4, so we'll be using that. But first we'll take the partial of u with respect to x, we get 1. The partial of v with respect to x, we're going to get 5. And the partial of w with respect to x, we're going to get 3y. And since y is equal to 4, that's going to be 12. Okay, now we need the partials of r with respect to u and v and w. So partial of r with respect to u, well, we have to use the chain rule here. The derivative natural log of something is 1 over the something, and then the chain rule tells us to multiply by the derivative of the of u in this case, and so the derivative of u of the inside of the natural log is 2u, so we get 2u over u squared plus v squared plus w squared. Similarly, for the partial with respect to v, we're going to use the chain rule and get 1 over u squared plus v squared plus w squared times the derivative of u squared plus v squared plus w squared with respect to v, and that's going to be 2v. And finally, the partial of r with respect to w, using the chain rule again, derivative natural log of everything is 1 over everything, which is 1 over u squared plus v squared plus w squared, then times the partial of u squared plus v squared plus w squared with respect to w, which is 2w. So now we need values for u, v, and w, which we get by using the fact that u is x plus 3y, and x is 4 and y is 4, so we get u is equal to 16. V is 5 times x, so it's 5 times 4 minus 4, which again is 16. And w is 3 times x times y. So 3 times 4 times 4, which winds up being 48. It's going to be more useful to view it as 3 times 16. We'll do that in a minute. So this is dr partial of r with respect to u is 2 times 16 over 16 squared plus 16 squared plus, and w is 3 times 16, so w squared is the quantity 3 times 16 squared. Now we're going to be able to do some factoring and canceling. Okay, we can, out of the denominator, we can factor out 16 squared from each of our 3 terms in the denominator and get 16 squared times 1 plus 1 plus 3 squared. And so we're going to be able to cancel a factor of 16 out of both the numerator and the denominator and get 2 over 16 times 11. But again, we can cancel a factor of 2 out of the numerator and denominator and get 1 over 8 times 11, or 1/88. And a similar process is going to give us 1/88 also for the partial of r with respect to v. And finally, partial of r with respect to w is going to simplify to 3/88. Okay, now we're going to plug everything into our main formula here for the partial of r with respect to x. And we're going to get partial of r with respect to u, which we found to be 1/88th, times the partial of u with respect to x, which we found to be 1, and then plus the partial of r with respect to v, which again was 1/88th, times the partial of v with respect to x, which we found to be 5, plus the partial of r with respect to w, which we found to be 3/88ths, times the partial of w with respect to x, which we found to be 12. And adding all this up, they all have the same denominator, so we add the 36 and the 5 and the 1, and we get 42/88ths, which reduces to 21/44ths. 21/44 is our partial of r with respect to x, and that leaves you to do partial of r with respect to y.